It's math time with Heinz. It's math time with Heinz. It's math time.
Hi everybody, welcome to this video where we're going to review everything we've learned about complex numbers thus far. So number one here says, look at the graphs of the following quadratic equations to determine if there's two real, one real, or two non-real zeros. So I already graphed these just for the sake of time. So when you type this in, remember we look on the x-axis for our real zeros. That's where my real zeros live. My real zeros live on the x-axis, and there's two. They're not nice numbers, but this has two real zeros, which tells me the b squared minus 4ac is positive. My discriminant is positive. This next one, notice it never hits the x-axis. Notice this next quadratic here never equals 0, so there's no real solutions here. There's no real solutions. That tells me when I solve this, I'm going to get two complex solutions with i's popping up. And finally, this one here, you'll notice it hits the x-axis once, so this has one real solution. But it's repeated. It's a repeated 0. X equals -2 is a repeated 0, which is why it bounces off the x-axis from there. So again, this is when your b squared minus 4ac is 0. And when do you get complex number solutions? Well, I have to take the square root of a negative number. So that's when my discriminant is negative. So you should be able to quickly check on your calculator whether a function has real zeros or complex zeros. And you should also be able to solve for those zeros. So solve these quadratic equations expressing your answer in a plus bi form. So let's use the quadratic formula. X equals -2 plus or minus the square root of 2 squared, which is 4, minus 4 times 1 times 5, all over 2 times 1. So then you type what's under the radical into your calculator, and in this case you get -16, which makes sense because I'm going to have complex numbered solutions. Well, the first thing I'm going to do is take out that factor of I. Sorry for the choppiness there, guys. The recording stopped. So I took out that factor of I and got 4i. And I got x equals -2 plus or minus 4i over, and I'm going to divide each of those by 2. I'm going to split that fraction up there. Divide by 2, divide by 2. So my final answers are -1 plus or minus 2i. And I wrote it as real plus imaginary, so I'm good to go. This next one here is not equal to 0, so I need to set everybody to the same side of the equation. So I get x squared minus 6x plus 17 equals 0. So I moved and collected all the terms on the left-hand side of the equation there. So now let's use the quadratic formula. X equals -b plus or minus the square root of b squared, square that in your head, minus 4 times a times c, all over 2 times 1, which is 2. So again, sorry I don't have my calculator pulled up, but I'm going to type in my discriminant. I'm going to type in what's under the radical, 36 minus 4 times 1 times 17, and I get -32 as my discriminant. Java update, great. X equals 6 plus or minus the square root of -32 all over 2. So I know I have complex numbered solutions because I have that negative in my radical. So I'm going to take out a factor of I to get rid of that minus, that -1. And then I'm going to tear apart 32 as 6 times 2. So 4 radical 2i is what I'm going to replace that with there. So I get x equals 6 over 2 plus or minus 4 radical 2 over 2i. Right, I split up that square root and made that substitution. So my answers are 3 plus or minus 2 radical 2i. And that are the solutions to that equation. All right, this is not equal to 0, so I'm going to add 7 to both sides. Plus 7 equals 0. And then I'm going to not even try to factor. I'm just going to jump right to the quadratic formula. X equals -2 plus or minus the square root of b squared minus 4 times a times c, all over 2 times a, which is 6. So then in my calculator here, I'm typing in 4 minus 4 times 3 times 7. 4 minus 4 times 3 times 7. I got negative 80. So let's deal with negative 80. Well, I'm going to take out the I, and then I've got to think of what perfect square divides into 80, and I'm going to do it wrong. Some of you might have said 4, which is fine, but then you got to tear 20 apart, which gives you 2 times 2 radical 5i, which is 4 radical 5i. So notice if you realize it's bigger than 4, 4 is not the biggest perfect square. You might have to do a bigger perfect square. 16 and 5 is actually the correct answer, even though there's not really a correct answer here. So I made that substitution and I split the fraction up. So my solutions are negative 1/3 plus or minus 2 radical 5/3 I. And those are my zeros. And finally, the last quadratic formula practice. I'm going to distribute that 2 through. So I get 4x minus 2 equals 5x squared. And I like dealing with positive x squared, so I'm going to move those terms over. So I'm going to subtract the 4x and add the 2. So I know it's easier to move the 5 over, but I like dealing with a positive x squared. So we plug it in, x equals negative b plus or minus the square root of b squared, make sure that number's positive, minus 4 times a times c, all over 2 times 5, which is 10. So we type in our discriminant and find out what our discriminant comes out to be. I'm going to try to do this in my head, but I'm just going to pick up my calculator just to be safe. I get negative 24 over 10. So how do I deal with negative 24? How do I split that up? Well, 24i, which is 4 and 6, so 2 radical 6i. So 4/10 plus or minus 2 radical 6 over 10i. And then finally, we get 2/5 plus or minus radical 6/5 I as our solutions when you simplify those fractions. So hopefully you notice that these are kind of the same process over and over and over again when using the quadratic formula. Let's practice some work with complex numbers. The key thing you have to remember, I squared is negative 1. I is this imaginary number whose square is negative 1. So find the value of this expression. So here's my game plan. Make a box, subtract the answer. So I kind of have 3 steps here, and we've done a couple like this already. X squared, xi, I squared. So this first box really comes out to be x squared plus 2xi, right? I have 2 of them. What's really I squared is really a negative 1. Minus whatever comes out from this blue box now. So now I'm going to make a blue box, x minus I, x minus I. X squared, negative xi, negative xi. Negative times a negative is positive, so positive I squared. So x squared minus 2xi, I squared is really negative 1. So finally, when I distribute to finish up my third step here, a lot of stuff drops out. X squareds drop out, 1 and negative 1 drop out, and I'm left with 4xi. Not too bad. Not too bad there. I squared equals negative 1. Number 4 here kind of has that same structure. Same structure. Make a box, and then subtract. That was supposed to be green. Oh, now it's galaxy. Now I have 2 galaxy pens. Go back to green. Thank you. So let's deal with this first box here. Find this product. 5, 2yi, 4 minus 3i. 20, 8yi, negative 15i. Oh boy. Negative 6yi squared. Good. So that really comes out to be what? 20. I can't combine anybody here because no one's like terms. I squared is my sign changer, so plus 6y, no exponent, minus, and I've got to do that all over again for the galaxy box over here. And no, I'm not switching to the galaxy pen. 20 minus 8yi minus 15i positive 6yi squared. So 20 minus 8yi minus 15i. Again, I squared is a sign changer, minus 6y. And now I get to distribute and change everybody's sign. So the first box I'm not touching. And now the second box, I'm changing everybody's sign. Minus 20 plus 8yi plus 15i plus 6y. So my 20s divide out, my 15s, and I'm left with 16yi plus 12y, but that's not real plus imaginary. This guy's real because there's no I attached to him, plus 16yi. That is a mess of a problem there. But notice it has the same structure as the one before it. Make a box, subtract. That's a really common structure New York State uses on Regents exams. So 12y plus 16yi. Number 5 here. If A equals that, B equals that, and C equals that, find A minus B, C. Well, I got to make a box for those guys first, because multiplication occurs before I do any kind of adding or subtracting. So what's really in that box is 4 plus 22i. This says negative 12i squared, but it really becomes positive 12 because I squared is a factor of negative 1. So what's really in that box there is 16 plus 22i. And I'm subtracting that from the number 3 plus 5i. So I got to do a little distribute. And then combine like terms. Negative 19 minus 17i. Okay, so that one wasn't too bad. You just had to find the product, then distribute that negative sign through. Last one here. Solve each of the following equations by factoring for all zeros. So I want to find all the zeros here. So again, all of our factoring techniques are still fair game. So I see a trinomial. So I need to figure out what multiplies to negative 27 that adds to 6. What multiplies to negative 27 that adds to 6? Well, that's 9 and negative 3. So I've got x squared in the front seat. All right, so this is the sum of perfect squares. So I'm going to treat it like dots, x plus 3, x minus 3, but I'm going to stick i's on to make that double negative become a positive there. And then 3 is not a perfect square, but I can still factor it. What number times itself is 3 is the square root of 3. So my zeros are plus or minus 3, plus or minus square root of 3. Those are the solutions to that equation. The graph of this will only hit the x-axis twice because only 2 of its 4 zeros are real. I got 4 terms, which means I'm grouping. Can't be too bad. Positive 25 gets taken out there. And it looks like I've got the sum of perfect squares again. So I think, all right, I know how to factor x squared minus 25. So I'm going to do x minus 5i, x plus 5i. It's just like if it was the difference of squares, but I'm going to stick an I on that second term. So my solutions are positive 3. 3 is the real 0. And then I have 2 imaginary zeros at 5i and negative 5i. Those are all my solutions. Okay, so factoring is basically the same as last time, except I can now factor the sum of perfect squares. And again, we normally don't do this, but sometimes it's a powerful thing to have in our back pocket. And we'll end with this question 7 here. Notice that you cannot factor this you can't factor this. Grouping doesn't work here. So use your graphing calculator to find the real 0. So I graphed it, and this is all I really saw, but I know the real zeros live on the x-axis, so it looks like x equals 2 is that real zero. Which means what is a factor? X minus 2 is a factor. So again, I graphed the whole thing here on Desmos to make it look nicer. So when you zoom out a little bit, you see x equals 2 is the only time it hits the x-axis, and then it goes that odd positive end behavior that I would expect. It goes up forever and down forever. So it only hits the x-axis once, which tells me I have some complex zeros hidden. So I know x minus 2 is a factor, so I can divide. I can divide by x minus 2. This is a terrible box. We're going to restart that. We're going to restart that there. There we go. I got x to the third, 6x squared, 9x, negative 50. So I should get a remainder of 0 because it is a factor. Let's see if I actually set up this question right. Yes, I'm at negative 16. How do I get to 9? I need 25 x's. So it does. So that tells me f of x equals x minus 2 times x squared plus 8x plus 25. So now my question is how do I find the complex zeros of that? What multiplies to 25 and adds to 8 is nothing. So let's find the complex zeros of that by using the quadratic formula. I know the real zero. I want to know where are the complex zeros. Where do they live? So x equals negative 8 plus or minus the square root of 64 minus 4 times 1 times 25 all over 2. All right, so then we type our discriminant into the calculator. 64 minus 100, I believe, is negative 36, which we know really is just 6i. So my solutions come out to be, my complex zeros are negative 4 plus or minus 3i. So I get all my zeros. I have x equals 2, x equals negative 4 plus 3i, and x equals negative 4 minus 3i. Those are all of my solutions. So hopefully this is a good review of everything we've learned kind of this year and how complex numbers can pop up.